All right, guys, for the second part of lesson 10.1, we're going to focus on two things here. This will be a little shorter, I think, than part one, but we're going to focus on making a tree diagram just to help us out with probabilities, and then we're going to get into conditional probability, which can be a little bit of a tougher area when it comes to these types of things. But we're going to start out with tree diagrams. Now, the tree diagram that they had as an example is a good one, but it's a bit abnormal. So I wanted to start you out with one that was maybe a little more traditional, and then we'll take a look at the one that they did. So I created my own here. We're going to make a tree diagram and set up some probabilities when it comes to this guy, and I'll give you some sample questions for what you could be asked along these lines, but you'll see that making a tree diagram really helps identify your possible outcomes, and working with probabilities really makes that a lot simpler. So you might have seen a tree diagram before, maybe you have, maybe you haven't, but let me kind of explain it as though you've never seen it before. A tree diagram is best used when you are working with 2 or 3 events, typically, right? You wouldn't use it for one event. There's no need for a tree if you're only doing one event, right? So it's really used for multiple events, but it's not good for cases where you have a ton of outcomes because your tree would be huge. So if you wanted to talk about a probability with rolling 2 dice, well, that's 2 events, but they have 36 outcomes with 2 dice. It would take you a long time to create a tree diagram for all the probabilities for 2 dice if there are 36 items in your sample space. And so that would be way too huge. So tree diagrams are best used for when you have a couple events, 2 or 3 typically, and you don't have a huge sample space. So take a look at this one. So we have jar A, we have jar B. So these are going to be our 2 events, is selecting a marble from each one. So we got red and blue marbles in there. So if I just was to reach into jar A and pull out a marble. So this first event, this first level of the tree is just going to be jar A. So I'll give it a little title here. The number of branches that you create is dependent upon how many types of outcomes are there. If I reach into jar A, I'm either going to get a red or a blue marble, so I only need 2 branches, one for red and one for blue. So you could have more if you had more colors in there. So we're going to call this our red branch, and this can be the blue branch. So what's the probability that you reach into jar A and pull out a red marble? Well, there's 3 red out of the 7. So 3 out of 7 chance that it's red, 4 out of 7 chance that it's blue. All right, so there's the first event. Second event coming off of those is now we're going to reach into jar B. So if I had reached into jar A and picked a red marble, here's what could then happen on my second event. So the second level here is all going to come from jar B. And again, let's just look at jar B and see what the potential outcomes. That should say red, not read, but there's 2 red and 3 blue. So again, I'm either going to come away with a red or a blue marble, right? And the same would be true if I were to reach into jar A and pull out a blue marble. I'm still going to have the options of red or blue from jar B. So let's look at those probabilities. So in the second jar, there's 2 red and 3 blue, so 2 out of the 5 marbles are red. And 3 out of the 5 are blue. So it looks something like this. One thing I would notice is that these must be independent events, because whatever happens on jar A has no impact on what I get from jar B, because they're 2 separate jars. This would change if I said I was going to reach into jar A and get a marble, and then reach into jar A again and get another marble. Those would now fall under the category of dependent events, because now your second one would definitely be affected by the first one. But these are 2 separate jars, so they're not going to affect each other. So independent events, if we look at our sample space, I could either get red, red, I could get red then blue. Could get blue then red. Or maybe they're both blue. All right, so that's our sample space. And it's always good to throw in the probabilities for each of your sample space items. So the probability that they're both red, if we just multiply those guys together, would be 6 over 35. Red-blue would be 9 over 35. Blue-red, we're looking at 8 over 35. And then we got the blue-blue case, which is 12 over 35. Okay, so there's the complete tree. So the purpose of doing that would now be, what if they ask the question, what's the probability that they're both red? Well, obviously we already have that figured out. What's the probability that they're both blue? We already got that figured out. What if they said, what's the probability that you get exactly one red marble? Well, find the cases where you got exactly one red marble, and we would add those together. So it becomes 17 out of 35. If they said at least one red marble, and we would add all three of those together, because all three of those contain at least one red marble. So with this layout, you can now answer all these different questions that they could potentially ask you, and it'd be super easy because you've already done the hard part, which is to identify all these probabilities. One thing you should know too is if you look at all four of these, of course, if you add those together, they should add up to 35 out of 35. When you have a sample space, it should represent 100% of your outcomes, right? All possible outcomes. So that's the gist of it, and this is, again, like I said, a pretty traditional standard type of a problem for this. Now let me show you the one that they had as an example, because it is a little bit different. I'll try to zoom in on this a little for you in case you don't have these notes. There we go. Okay, so again, you have these two jars, jar A and jar B. Jar A contains these different types of cookies, chocolate chip, peanut butter. Jar B has one single chocolate chip cookie left in it. We select a cookie at random. What's the probability that it's a chocolate chip cookie? So one thing you got to consider on this, and this is one where here's kind of the first trick of this problem. Where are the two events? Because the way that this reads, it almost sounds like there's only one event. I'm picking a cookie, right? But because these are separated into two separate jars, the first event is which jar are you going to pick from, right? A or B. And so we have to first pick a jar. Which jar are we going to pick a cookie out of? And so that created the first level of their tree. Is it going to be jar A or jar B? And of course, those would be equally likely to happen. They're both 50%, right? 50-50, then I'm going to pick one of the other jars. Then the breakdown comes by cookie, right? So then if you looked at jar A, here's the breakdown of the cookies from jar A. I would not have written it as all 4 cookies. To be honest, I would have had just 2 branches. It's either chocolate chip or it's peanut butter. And I would have thrown in the branches for each cookie separately like that. Right? So I would have said chocolate chip. I would have said, well, 2 out of the 4 are chocolate chip. So 0.5. 2 out of the 4 are peanut butter. So 0.5. So I would not have had 4 branches right here. I would have had 2 branches, 1 for chocolate chip and 1 for peanut butter. I don't know why they would want to lay out all 4 of those, because if you had a whole bunch of cookies in there, that tree would get real ugly really fast. So I wouldn't spread them out. It's better to do them in like groups, like the way we did the first one. So anyway, so there comes the layout, and now so they say, okay, so select a cookie at random. What's the probability that it's chocolate chip? And so as you look at the end results here, this is your sample space, right? Like I said, I would have done this, and let me just throw it out there. I would have said from this one it's either chocolate chip or peanut butter, where 2 out of the 4 are chocolate chip and 2 out of the 4 are peanut butter. So then I would have multiplied my 0.5 times 0.5 to get 0.25. Same thing here. And so I would have had 3 items in my sample space, right? So I would have had chocolate chip from jar A, peanut butter from jar A, chocolate chip from jar B. Those are the 3 potential results that you could get. And if you add those 3 decimals together, they add up to 1. So we know we're in good shape. So that's really the way I would have done it. The question on this was, what's the probability that it's chocolate chip? So now you just add up the chocolate chip options, right? So it could have been chocolate chip from jar A or chocolate chip from jar B. So if you did your 0.5 plus 0.25, we're looking at 0.75. So 75% chance you're coming away with a chocolate chip cookie. Hopefully that's the one that you wanted. So now let me move on to the final part, which is conditional probability. Let me give you the main idea behind conditional probability. Conditional probability is a case where they ask you a probability question, but then they give you more information. They add in a condition that changes your sample space. Let me give you a really easy example. If I were to ask you guys, hey, guess my birthday, right? What's the probability that you guess my birthday correctly? It'd be 1 out of 365, right? But what if I said, guess my birthday, given that it's in the summer? Well, that would change your sample space, right? Your denominator would no longer be 365. It would be like 90, right? However many days are in the summer. So when you're given a condition, like I told you the condition was that it's in the summer, then it changes your sample space. Typically it shrinks your sample space because you now know more information, right? And so if I know more information, my chances are better of getting it right. So a couple formulas. We already talked about these 2 up here. So when we were doing independent events, as you guys already saw, we were simply able to multiply those 2 events together, right? We just did that with tree diagrams. We multiplied from left to right those independent events. When it comes to conditional probability, we're going to look at something like this. So here's the way that you would read this formula. This is the probability of event B given that event A happens. So the probability question is the first guy. What's the probability of event B happening? The second guy is your condition. This is the given information. And just like the birthday question I threw out a second ago, notice that your given becomes your sample space, right? It becomes your denominator of the problem. When it comes to the numerator, the probability of A and B, well, just think about this logically for a minute. I'm asking the probability of B happening, so naturally that has to be a part of it. But now I also know the condition of A happening. So whatever goes on top, my desired outcome, has to be true about both. It's got to fit the condition and address the probability question, right? So when you looked at, like, what's the probability of guessing my birthday, right? And I said, given that it's in the summer, well, your desired outcome can only come from the summer days, and it has to be the day of my birthday. So both of those statements have to be true for the numerator. So let's look at a couple. Let me just mention this. We talked about this before, but let me just throw it out again. When it comes to this formula, understand that if the events are independent, this condition wouldn't matter because they're independent anyway. So if I said, what's the probability of B happening given that A happens? Well, if they're independent events, it doesn't matter what happens in event A, right? The probability of B is still the probability of B if they're independent events because it's not affected by event A, right? And so that's what they're trying to tell you with this formula. Like I said, we don't use this one a ton. It's kind of more better for explanation. So let me take you down to some practice problems. So I just changed the example that I had in here. As I kind of looked through it, it wasn't the best example, so I altered it a bit. So anyway, so we're going to look at the tree diagram that we filled out earlier. So I'll bring that one back in, but we're going to say, okay, what's the probability of selecting a red marble given that, so here's my condition, given that both marbles are not blue. So it's kind of like you're not going to get the blue case. So what's the probability that you have exactly one red marble? Exactly one. So guys, do read these at face value. So if it says you got one red marble, you get one red marble, right? It doesn't say at least one red. It just says one red. So they mean a case where you get exactly one red marble. So again, here, let's look at the tree real quick. If I just said, what's the probability you get one red marble? Well, we would just add those two together, right? And it would be 17 out of 35 because 35 was the total possible scenario of all of my sample space. So that's why it was out of 35. But when you're given a condition, they're giving you more information. Remember, it shrinks your sample space, right? They basically said it's not this case. So then what's the probability, or how does that affect the setup that we would use when we're setting this up? I encourage you to get comfortable with the formula because it does help in a lot of the tougher cases. It helps to just stick with the formula. So let me lay this out here. So what's the probability that you get exactly one red marble given that you did not get the blue case? So we did not get the blue case. Whenever you set these up, a great place to start is your denominator, right? So you look at your given information, and we're going to figure out what our sample space is. That goes on bottom. So in this case, it's knocking out the blue case, right? So what's left in terms of probabilities if this guy got eliminated? So if I know that, okay, it can't be the blue case, well, then my sample space becomes those three cases, right? So my answer is going to come from one of those three cases. This becomes my sample space. So if you add those together, let's see, 15 plus 8, 23 out of 35. So 23 out of 35 becomes your sample space. As far as the numerator is concerned, remember it's both conditions taking place. Our desired outcome is the fact that I get exactly one red marble and do not get two blue marbles. So if I said, okay, well, which ones of these fit that description? So where's the case where you get exactly one red marble and not two blue marbles? It would be those two cases, right? So if I add those together, 17 out of 35 becomes our numerator. And if you just think in terms of multiplying by the reciprocal, the 35s get knocked out, and it's just 17 out of 23. So again, notice the main thing that got changed on this was the denominator, right? It was no longer out of 35 overall. It's technically out of 23 because there was 23 ways of not getting two blue marbles. Let's do another one. Last one. All right, so if your marbles are the same color, what's the probability that your first marble was red? So I specifically wrote this one this way to try to cover up the given information a little bit. So notice they don't always use the word given. Okay, but somewhere in here you have to understand, hey, there's a given condition under this that changes my sample space. And in this case, they're telling me that the marbles are the same color, right? So that becomes my new sample space. So this is our condition, our given information, that becomes our new sample space, right? If we know that they're the same color, then that's all I have to choose from. So it says find the probability that your first marble was red. So again, if I just stick with the formula, and you might be able to figure this out without a formula, but there's going to be some tougher cases, so I'd like you to get familiar with the formula. Okay. So what goes first? What's the probability statement here? The first marble was red. So the first marble was red. And what was our given? The given is your marbles are the same color. So that's the way that we would see that as kind of the setup. So again, I always start with the denominator. Start with my sample space, so they got to be the same color. So what's the probability that the marbles were the same color? Right, obviously it's the case right here and it's the case right here. So those two are my sample space. So if I add those up, I'm looking at 18 out of 35. That's our sample space. And if that's my sample space, that means my numerator has to come from those cases. That's why they throw in the word and, right? It can only come from one of those two cases that I just identified. So as far as the numerator, the first one's got to be red, and they got to be the same color, because that's my sample space. So where do we obviously see that one? So here's the only case where the first one is red and they're the same color. So it fits both scenarios. So that 6 out of 35 is the only case that fit both scenarios. It fits the probability and the given condition. Right? And again, you can knock out the 35s, you get 6 out of 18, which is obviously 1/3. Okay, so that's it for that one.